So far we've been studying series circuits. That's where all the components in a circuit are combined in one path with the voltage source. So when one component is receiving electricity, all of them are receiving electricity. And where those are probably the simplest circuits, they aren't always the most useful. So if I think about Christmas lights, when I was a kid, the Christmas lights that my family had were really annoying because if one bulb burnt out, the entire thing went out. Okay, and so what happened was one bulb would burn out, and so it was no longer part of the circuit. It caused a gap in the circuit, or made the circuit open. That's the word we used for a circuit without electricity flowing through it. And if you have an open circuit, none of the circuit is receiving electricity, if you remember. And so now, if none of that circuit, if none of the string of lights is receiving electricity, none of the bulbs are on. So one of them is burnt out, and there's 149 other ones that aren't burnt out, but you have no way of knowing, right? That's horribly annoying. Strings of lights these days are wired in parallel. And so when one light burns out, they don't all go out. They all still work except for that one. And so it's not that parallel circuits are an improvement to series circuits. In that application, they are an improvement to series circuits, but they have to be used in conjunction with series circuits depending on what you want to do. So if you want your phone to have the screen on and be sensing how you're holding it so that it can rotate the screen, you want the gyroscope sensor and the screen light to operate at the same time. And so those should be wired in series with each other. Now, it's more complicated than that. A circuit board works in a very complex way. So it's not just, is it in series or is it in parallel? But for the sake of simplicity, we can think of it that way right now. So we're going to talk about how a parallel circuit works. So we started with series. We're going to talk about just parallel, and then we're going to combine the two, combination circuits. So with series circuits, we had to remember that the current passing through one component is the same as the current passing through all components. There's only one path for the current to follow, and so it's got to go through all the components. That's the first thing. The second thing is that the equivalent resistance of the circuit is calculated just by adding them all up. So the total resistance of the circuit is just as if you took all the resistors and smushed them into one big resistor. The third thing is that the potential difference in the voltage source is the same as the potential drop around the entire circuit. Okay, and so if it's a 24 volt battery, that means that over the course of the circuit, that 24 volts has to be dropped across each of the components. Those are three things that we have to remember about series circuits. The rules are a little bit different for parallel circuits, and they're a little bit more complex. So pay close attention and make sure you do the practice afterwards. So here's an example of a parallel circuit. We have a voltage source just like before, and we have current coming out of it, and the current doesn't have just one path it could follow. It either is going to go through this resistor, or this resistor, or this resistor. Now, when I say the current is either going to go through one or the other, I'm not talking about the full current. Each branch is going to receive some current, but each electron has to choose a path to go down. Now, the electron doesn't have a brain, and so it's not really choosing which path to go down. It's all about which branch, this is a branch, this is a branch, this is a branch, which branch has the most resistance to current flow, which branch has the least resistance to current flow, and the number of electrons that pass through each of those branches follows kind of that proportion. The easiest one will get the most current, the hardest one will get the least current. So this is kind of what your run-of-the-mill parallel circuit would look like. Multiple branches for current to go through. And so we can treat each of these paths as an individual circuit. So the voltage is being applied in this circuit, or in this circuit, or in this circuit. Let me put some colors on those things. So we have circuit number 1 looks like this. Circuit number 2 looks like this. And circuit number 3 looks like this. Okay, now for each of those, the total voltage increase at the source has to equal the total voltage decrease in the circuit. So if this voltage is, say, 12 volts, that means that the red circuit has to drop 12 volts, and the green circuit has to drop 12 volts, and the blue circuit has to drop 12 volts. So it's not that that voltage drop is going to be split up among the different resistors, it's going to be applied across each resistor, or each branch. Now, that's different than the series ones. The series ones, it was just the sum of the voltage drops was equal to the total voltage increase. That's not the case here. We can also look at the current differently. So all the current, let's say 5 amps, is coming out of this battery, 5 amps. That 5 amps, part of it is going to travel through the red circuit, part of it is going to travel through the green circuit, and part of it is going to travel through the blue circuit. It's going to split up at each of these junctions. So here's a junction right here that will take you down the red circuit. Here's a junction right here that will either take you down the green or the blue circuit. Okay, so if we've got 5 amps of current, some of it's going to go here, let's say 2 amps, some of it's going to go through here, 2 amps, and some of it's going to go through here, 1 amp. And the 3 of them together have to add up to the total. So when they all come back together, which is right over here, at this spot right over here, you should have 5 amps again. Okay, so current works differently as well. The current is not the same through each of the resistors. The total current of each of the branches is equal to the total current coming out of the battery. Okay, the third thing that's different is how we add up total resistance or equivalent resistance. So we'll go in depth a little bit more and see how each of those things works. First, we have Kirchhoff's current rule, or Kirchhoff's junction rule. Kirchhoff is Gustav Kirchhoff. He's a German physicist. It states that the sum of the currents going into a junction has to be equal to the sum of the currents leaving the junction. So if we look at our example up here, here's a junction. So the currents going into this junction, that's 5 amps altogether, have to be equal to the total current leaving the junction. So we said that this was 5 amps going in, 2, 2, and 1 in each of these branches. So that means going in you've got 5, going out you have 2 going into the red, and 3 left in the green and blue together. Okay, so that would be Kirchhoff's junction rule. Whatever current is going in, you've got to have the same current coming out in whatever branches they are all together. So that would give us total current, or total current going into a junction, has to be equal to I1 plus I2 plus I3, etc. Now the formula there, I total equals I1 plus I2 plus I3, that's not the clearest way to think about it, but it's the clearest way to write it, unfortunately. So it's saying that for any junctions, the current going in has to be equal to the current going out. Now we can also think of it like this. In the case of this particular circuit, the total current here has to be equal to this current plus this current plus this current, because those 3 currents add up to what there is at this junction. Same thing over here. Okay, So all the branch currents add up to the total current. That's another way of thinking about it. The second one is the potential difference across all branches have to be equal. Okay, so what we said before was that the total voltage has to be dropped in every path. So the red path here, one electron is going to follow this path. And that particular electron, let's call him Steve, he has to lose all of his potential energy in that path. Okay, Steve is only going through one path, and so he has to lose all of his potential energy in that path. Margaret maybe didn't choose red path, maybe she chose green path. She also has to lose all of her potential energy through that path. And so each branch has to drop all of the voltage. Now, I shouldn't say each branch. Each path has to drop all of the voltage. Okay? Because each electron has to lose all of its potential energy. If only a portion of that potential energy was lost in this resistor, then Steve would still have energy coming out the other side. And if this spot over here is a spot of zero potential, it doesn't make any sense for him still to have potential energy when he reaches this side. Okay? So the potential difference rule, or the voltage rule, is that the potential difference across all paths are going to be equal. So we can say then that VT is equal to V1, which is equal to V2, which is equal to V3, etc. Okay, that's the voltage rule. When you look at any path, in that path, all of the voltage has to be dropped. Now I say path because when we do combination circuits, we're going to see that in a single path there could be series components and parallel components. And then you have to be a little bit careful about which order you do things in. The last thing is equivalent resistance. And so it was discovered that in a circuit like this, the more branches that you added, the less total resistance there was in the circuit. So if you had one resistor connected to the battery, the total resistance of that circuit is that one resistor. But if you added more branches with resistors in them, it turned out that the total resistance in the circuit went down. And so we have a very odd rule for total resistance, or for equivalent resistance. And it looks like this. 1 over equivalent resistance, or the reciprocal of the equivalent resistance, is equal to the reciprocals of all of the resistors that are connected in parallel with one another. 1 over R1 plus 1 over R2 plus 1 over R3, etc. Now, you might ask, why can we not just flip that upside down? Wouldn't it be the same as equivalent resistance is R1 plus R2 plus R3? No. You can try it yourself. Fractions don't quite work that way. So if you were doing 1 over the equivalent resistance, and I'm going to pick numbers that are pretty simple, hopefully, is 1/2 plus 1/4 plus 1/8. Okay, if we would flip this upside down, just as it is, and go 2 plus 4 plus 8, you're going to get 6 plus 8, which is 14, right? So then we'd get a resistance of 14 ohms. We're going to find that that is not correct. So now when we add half plus 1/4 plus 1/8, this is 4/8 plus 2/8 plus 1/8. That's 7/8. So 1 over the equivalent resistance would be 7 over 8. And then when we flip that upside down to figure out what the equivalent resistance is, you get the equivalent resistance is 8 over 7 ohms. 7. That's not the same. So let's do a couple examples here. Using the following circuit, calculate equivalent resistance, potential difference across each resistor, and current through each resistor. So we'll start with A, the equivalent resistance. So we decide what kind of circuit this is, series or parallel, by deciding, does everything have to go through one path, or are there multiple paths for current to flow through? So if we're looking at current traveling this way, again, it does not matter which way you go. Once you reach here, current cannot go through both paths at once, or I should say, a single electron cannot go through both paths at once. It's got to go through one of them or the other. It's got to choose one. Okay, and so because there's multiple paths to follow, that means this is a parallel circuit. And so we need to calculate the equivalent resistance using these two resistors calculated in parallel. And so our formula for equivalent resistance for resistors in parallel is 1 over Req equals 1 over R1 plus 1 over R2. There's only two resistors in this case. So 1 over the equivalent resistance is equal to 1 over 6 plus 1 over 4. Now you can do this mentally. You can make them a common denominator and add fractions that way, but in the end, when we're solving larger circuits, you're going to just want to use your calculator to do this. Okay, and your calculator has a fractions button, and it will do everything for you. So I think you should get used to doing that rather than doing all the mental work for this thing, though it is good exercise. So 1 over Req is equal to, so this is 2/12, this is 3/12, so that's 5/12 in total. And then when we flip that upside down, because we don't want the reciprocal anymore, we get 12 over 5 ohms. You can change that to a decimal if you want, but I'm going to leave it 12 over 5 ohms. Okay, so we've figured out the equivalent resistance of this circuit. Notice that this equivalent resistance is smaller than any of the individual branch resistances. So 6 ohms, this is half of that. It's a little bit more than half of that. 4 ohms, this is less than that as well. So you can do a simple check to see if you've got it right by checking to see that your equivalent resistance is smaller than any of your individual resistances. That won't tell you that you've got it right, obviously, but if you have a resistance that's larger than any of your branch currents, then you know that you've got it wrong. B, the potential difference across each resistor. Okay, so we know that in each path, the voltage has to be all dropped. So we've got a 12 volt increase at the source, which means we need a 12 volt decrease in each branch. So R1 is one branch, and R2 is another branch. So we can look at it like this again. Here is one circuit or one path that can be followed. And here is the other path that can be followed. Okay, so in each of those paths, all of the voltage needs to be dropped. And so we can say that the total voltage, 12 volts, is equal to V1, and that's equal to V2. So that's 12 volts. So V1 is 12 volts, the full 12 volts has to drop across the first resistor, and the full 12 volts has to drop across the second resistor. Finally, the current through each resistor. We can use V equals IR, Ohm's law, for each resistor, even when we're working in parallel. So with this resistor, we're going to use V1 equals I1 R1. And we know the voltage, we know the resistance, so we can figure out the current. So the current is V1 over R1, which is equal to 12 volts over 6 ohms. And so the current through branch number 1 is 2 amps. Now we can do the same thing for I2. I2 is that 12 volts divided by 4 ohms, which gives us 3 amps. So we have now found that more current is going through R2 than through R1, which should make sense because resistance is resistance to current flow. That's why it's called resistance. And so if there is more resistance to current flow through R1, less current is going to go there, right? If there is less resistance to current flow, more current is going to go there. And so that brings us to another tool that we can use, proportions, to figure out how much current is going through each of the branches. Because we know that current is inversely proportional to resistance, higher resistance means lower current, then we can use just fractions or proportions to figure out how much current is going through each branch if we know the current that's going into those branches. So we've got 2 amps going into this junction over here. That 2 amps is going to split top and bottom, and it's going to depend on how much resistance there is in each of those branches. So the bottom branch has 20 ohms of resistance, the top branch has 10 ohms. So R1 is twice as easy to go through as R2 is. And so that means twice the current is going to go through R1. And so we can use algebra to figure out how much is going through each of them. So first of all, the total current is 2 amps. And the total current has to add up to I1 and I2, right? The branch currents have to add up to the total current. So IT is I1 plus I2. Okay, we also know that I1 should be twice I2, right? We just said that it's twice as easy to go through that one, and so the current going through I1 is going to be twice as much as what's going through I2. And so we're going to just write that here. I1 is 2 times I2. And so we can sub this into this formula over here. So IT, total current, is going to be equal to 2I2 plus another I2. So that's 3 I2s. So the total current is equal to 3I2. And since we know the total current is 2 amps, then we can solve for I2. So divided by 3, I2 is 2/3 of an amp. Or 0.6 repeating. Okay, so if we know that I2, or the difficult branch, has 2/3 of an amp, then the easy branch has twice that. Okay, so I1 is twice I2, so it's 2 times 2/3 of an amp, and that gives us 4/3 amps, or 1 1/3. So that's I1. So we could have solved that a different way. There's more than one way to figure out the currents through each of those branches. We could have figured out the equivalent resistance first, and then we could have figured out the total voltage, and then gone through that path to figure out the current through each of the branches. But we can also just use proportions. We know that twice as much current is going through the 10 ohm resistor, and so we can use just some algebra tricks to get to what the current is.